Hejsa.
And welcome to Context Free, where we talk about programming languages. Today I want to talk about multidimensional arrays, sometimes called tensors, such as when they're used in deep learning frameworks like TensorFlow or PyTorch. In these frameworks, you'll often deal with four-dimensional arrays. For example, you'll have the height and width of each image, along with red, green, and blue channels, and various channels also exist that are learned throughout the network. And furthermore, beyond these three dimensions, you'll also be working with batches of images going to the network all at once for a fourth dimension. We often deal with two-dimensional or other data as well. And today we'll focus on two-dimensional data because it's simpler. So for example, we might have different test or exam scores down rows and multiple students across columns. And we can do various aggregate calculations, such as we can see the average across all students for a particular test score and replicate that for each row. We can also do an average down columns and replicate that as well. So now we have a row, which is the average of the rows above it, and we have a column, which is an average of these columns. And different exams or students might have different mean scores, which might be based on a variety of factors. This is one way of analyzing multidimensional data and working with it. This kind of batch look across different dimensions is also common in deep learning. In statistics, we also have things called marginal distributions, where we sum across one axis or another. But worth pointing out that our multi-dimensions of our axes for our arrays is different from the dimensions of space for a vector. So for example, with two values, I can describe a point in 2D space. Or with a three-dimensional vector or three values, I can define a point in 3D space. That's different from a 2D array where I have two axes along which to measure. Any one test here gives me a 3D point, or any one student gives me a 2D point. Worth keeping that issue figured out. There's also something else to look at. Sometimes multidimensional arrays are called tensors, such as what we see right here. There's also a formal mathematical definition of tensors that have certain types of operations defined for them. And that's not usually how things like TensorFlow or PyTorch reference the word tensor. And so today, if I use the word tensor, I'm just meaning a multidimensional array. When we talk about multidimensional arrays, there's also the topic of how many dimensions does it have? We already discussed ambiguity over that term. There's also terms like order, rank, or degree. So you might call a scalar a rank 0 tensor, or a vector a rank 1, matrix rank 2. People also might call it order or degree again. We'll come back to this later. But let's look at some code. In a previous video, by being lazy, I made a matrix a vector of vectors in C++. That's not a very efficient way to do it. Maybe we'll get back to this in C++ in a future video, but for now we're going to look at other languages. Starting in Python. This right here effectively is a vector of vectors in C++, only we'd call it a list of lists in Python. If we run this, we expect to see this list of lists out. Notice I can have heterogeneous data in here. This is a float, and this is an int. I can also have heterogeneous sizes. Sometimes these are called jagged arrays or irregular arrays, versus regular arrays that have common sizes in each dimension, or each axis. And the most common way, perhaps, of doing multidimensional arrays in Python is with NumPy. So it's not built into the language, although there have been language changes made or encouraged because of the popularity of NumPy. And as
Troels
likes to say, library design is language design. Let's turn this into an nd array, which we can do with the array function. And first of all, we get an error here. That's because when it goes into NumPy, we need to have equal sizes for everything. It needs to be regular. So let's go get our other value back and try this now. And now we see that when NumPy outputs it, it knows it's in a grid. Furthermore, it's made all the types the same. And it promoted all the integers to floats because at least one float was in here. We can also get our mean row and mean column. Referred to as axis 0 and axis 1. Python counts indices from 0 in lists, and NumPy counts axes from 0 in its nd arrays. When I say I want the mean for axis 0, that means we're going to be reducing across axis 0 and making axis 0 disappear. If I want the mean for axis 1, I'm going to be going across axis 1, which is the second axis, and make axis 1 disappear. So this will give me the mean row, or the mean of each column. This will give me the mean column, or the mean of each row. So another thing to watch out for in a nomenclature. Let's see how this does. So here we get our 97, 86, 79. just like in our spreadsheet, and 84 2/3 and 90 for our column. But notice here, my output was a column and it was a row. But in NumPy, they both came out as individual rows. If I want to keep the original shape, I have to say keep dims equals true on it. If I do this and run it, now my column has been retained as a two-dimensional array, or a rank 2 or order 2 tensor, if that's what you prefer, and I have a column shape to my output. I could do the same with mean row, and it would be two-dimensional, but as a row. I can ask for the number of dimensions with ndim. So I'd expect to see two-dimensional, one-dimensional, because I didn't keep the dimensions, and then two-dimensional again. 2, 1, and 2. I can also select rows or columns. This gives me the first row, and this gives me all the rows for the first column. And again, we see our first row and our first column. Again, if I want to keep the original shape, I need to use a different style. In this case, I can say keep everything through the first column, and that indicates to it that it wants to have a range of columns that only happens to include one thing. And I can see that there. And instead of giving a beginning and an end, I can give a third element to my range, which will step across columns and give me every other one, 0 and 2. So this is just a small sampling of the kinds of ways you can work with multidimensional data in NumPy. And one other thing to look for here is how the data is stored internally inside of the scores array. I can ask for the number of bytes in the array, which is 8 for each float times 6 floats, or 48 bytes. I can ask for the shape of the array, which is 2 by 3, 2 rows and 3 columns. I can also flatten the array, and there's a number of ways you can do this. I'm going to use the ravel method. If we print this out, we see 95, 83, 76, 99, 89, 82. Because NumPy by default is row major. We see each row happening at a time, which feels somewhat natural for a left to right, top to bottom language. And just to prove that this is the internal data storage, I'm going to change one of these values. I'm going to change the element at 0, 1, 2, 3 to a different score. Let's say flat 3 equals 97 instead of a 99. Let's not print out just flat, but the original scores array. If we run this, we see that the 97 changed at index 3, and it also changed in the original array, because this new object still internally holds a reference to the data stored by the scores array. And finally, one other little thing on the term dimension, or rank, or order, or degree, in reference to these multidimensional arrays or tensors, is there's yet another definition for rank to watch out for. And that's the matrix rank, which we can get from numpy.linalg, or linear algebra. The matrix rank refers to how independent the columns and rows are from each other. So for example, my original matrix is a 2 by 3, which means the most independence it can have across row or columns is 2, because there's only 2 rows. Print this out, we see I have a matrix rank of 2. But if our second row is just a scale of the first row, which I can do just by multiplying 0.5 times the first row and assigning it to the second row, and let's print out what happens after we've done this so we can see it. We see that now row 2 is just half the first row, and our matrix rank is just 1, because it knows that the second row is just a scale of the first row. We're not going to get into the algorithms that define this, just trying to watch out for the fact there's lots of overloaded words when speaking about this topic. But I think we've seen enough Python. Let's move on to Octave/MATLAB. Here we have our same rows and columns as before. Let's prove that we're seeing it correctly. There we got it. I'm taking advantage of the lack of semicolon means an automatic printout over here. You don't want to leave this in an actual useful library or application most of the time. We can get our mean across axis 1 or axis 2. Remember in Python, we call our axes 0 and 1, but MATLAB or Octave is 1 based. So if we do our mean down axis 1, we see our mean row, or our mean across axis 2 across our columns, we see our mean column. And differently from Python, Octave stores its data in column major format. So we say flat equals scores of colon, which is shorthand for saying flatten this for me, please. We'll see it flattens it into a column vector as opposed to a one-dimensional row vector. And if we try to look for the dimensionality of these, we expect to see scores being two-dimensional. And flat, let's see what it is as well. If we run this, we see they're both two-dimensional because MATLAB and Octave are very matrix-oriented, and the smallest number of dimensions they're ever going to tell you something is 2. Another slight difference, in Python, if you want to build three-dimensional or more, usually you'll build outward. So if I wrap this again in another list, I'll have a three-dimensional array. But in Octave, the dimensions tend to go the other direction. So the first dimension is the rows, in other words, going down a column. Our second dimension is our column, meaning going across our rows. And later dimensions, dimensions 3, 4, 5, and so on, go after. So for example, even though that's only a 2D array, I can say, what's my score at row 1, column 2, and I expect to see an 83. But technically, we have arbitrary other dimensions behind that. If I wanted to make a 3D or 4D array, such as I showed earlier for the deep learning example, I might have dimensions going further back. So I can actually say, I want to go 7 dimensions deep into this array, but I only want the first of each of those later dimensions. And Octave's happy to give that to me, because abstractly speaking, every array in Octave is infinite dimensional. Also worth pointing out that arrays concatenate by default in Octave. So if I look like I have a nested array here, it doesn't mean anything special. It just expands that out as part of the array around it. On the other hand, it does not like having irregularity or jaggedness. And if I want to have heterogeneous arrays, I have to use something called cell arrays, which usually are made by wrapping your data in curly braces instead of square brackets. Except it still wants to have the same number of things inside of it. So for kicks, I'll wrap that in there. So I have 1, 2 in my first row, and 1, 2 in my second row. Only again, they're going to show me column major. And one other thing we should look at in Octave before we move on is how changing data creates new objects. So I can keep track of my old scores here. Then I can modify my scores. Let's change the element 1, 2 again to be an 85. And then look at the old and the new and see what happens. And we see here that the old, even after the assignment occurs, is still 83 in that position, even though scores has changed to 85. Because this assignment doesn't actually mutate the array, it creates a new array with that changed value. And sneaky behind the scenes, they use copy on write to make this efficient. But we'll have to go into that at a different time. Let's move quickly through some additional languages so we can get a little more sampling of the kinds of variety that's out there. This is Futhark, a purely functional language for data parallel execution. It can compile for use on your GPU, for example, and designed to be able to write efficient algorithms that can then be consumed by other languages. So here we have a 2D array of float 64s containing the same values as before, and we can do a mean of the columns or a mean of the rows. And this comment is for something called literate Futhark, which is one of the convenient ways to be able to see multiple expression values from a Futhark program. One of the cool things about Futhark is that they have explicit support for array dimensions in the types of your variables and functions. So this says I have n rows and m columns in the array that I want to get the mean column of. And to calculate it, I'm going to map each of the rows and then reduce that row by summing the row up from 0. So now I will have a sum of each row, or the sum column. Then I'm going to map that sum through division by the number of columns. And then the efficient way to calculate a mean row is just to transpose the array, or tilt it so the rows are now columns and the columns are now rows, and calculate the mean column of that transposed array. If we run this, it generates an output markdown file where we see our mean column and our mean row. In this case, back down to only one dimension, like what we saw in NumPy. We could have gotten fancier in implementation for mean row, but this is more code and less efficient than the transpose version. Let's see what else there is to see. This language is called APL, and I purposely showed it after Futhark because our style of getting the work done is going to be fairly similar to Futhark in some ways, but in a much more terse syntax. So the first thing we see is that assigning to our scores variable looks different than before. We have a different kind of syntax with this left arrow. We also list all of our data as if it were a single row, but we tell it using the row symbol, Greek letter row, that we want this to be a 2x3 array. APL inherently works on multidimensional arrays as its way of thinking about the world. Row can also be used as a prefix function where it tells you the shape of the array. So if we run this here, we see that we have our scores, and it's a 2x3 array. It also likes to print out the rest of the source program. When we're focusing on our output here, look at what's off to the left. sort of like what we saw in our output markdown from Futhark. We can also just look at the scores itself, where we see our two-dimensional array as expected. We can also ask for not only the shape of this array, but the shape of the array. Meaning if this gives us 2 and 3, this will give us the shape of the 2, 3 vector, which is 2, which is the number of dimensions in our array. We can calculate the mean row like this, which actually, like I said, is a whole lot like Futhark. In Futhark, we map the array, then for each row, we reduce that row by summing the values together. In this case, we're going down a column for a mean row, but the concept's very similar. This right here is one of the ways you describe a function in APL. The function will have up to 2 arguments, one on the right and one on the left, where alpha is to the left, or your first, and omega is to the right, or your last. This right here says reduce by summing the elements down the first axis, and this says get me how many there are. And if I take that sum and divide it by the number there, using our division, then we'll have the mean. So if we view this here, we'll see our mean row. And just like in Futhark, where we could define one as a transpose of the other, we could do the same thing here, transpose our array, and then find the mean row, which was our original mean column. And again, let's collapse it down to just a one-dimensional vector. But rather than either of these, we can do like we had in Octave and NumPy by calculating the mean across any axis, given as an argument to the function. So here when we say, please reduce, we're saying across which axis, whether that's axis 1 or 2, counting from 1 instead of from 0 again. So we'll sum across whatever axis, and then we'll get our shape, as described previously, and find the size of the axis by accessing index alpha from that size. So done this correctly, we should see the same as before, only now it works for arbitrary dimensions of arrays, whatever axis we specify. One other interesting thing about APL is that it has a different notion for jagged or nested arrays versus multidimensional arrays. So in this case, I'm going to be getting the rank, or the degree or the order, the number of dimensions in this array, which we saw was 2. But this right here, instead of being a two-dimensional array, is going to be an array of 2 arrays. So this array itself on the outside has only 1 dimension. On the other hand, there's a separate symbol here for array depth, which is how deeply nested are the arrays. So our original array is 2-dimensional, but does not have any depth beyond the single level. But this nested array, which could be jagged, is only 1-dimensional, but has a depth of 2. If we run this, we'll see that here. Yeah, the original one is 2-dimensional. Our nested array is 1, but our original array is only depth 1, and our nested array is depth 2. So before we finish, let's also take a look at R, which is a statistics language, and then back to Python again before we're done. R has plenty of interesting things we could say about it, and in some ways is like Octave. So for example here, this C makes a vector, and concatenating all these vectors together with C just makes them into a single vector of length 6. Also note that I put it in column major order, as opposed to the row major order we had in some of the other languages. This is back to being more like Octave as well. It's a bit like APL in that I have to specify the shape explicitly. One of the cool things about R is that you can name your rows and your columns. So let's run this. And we're back to the first time we have labeled rows and columns since leaving our spreadsheet. And if I want to access, say, a particular column of this 2D array, I can say, skip the rows, keep them all, and let's just get Alice. And we see here Alice now has a test 1 and a test 2 score of 95 and 99. You can also get means with these built-in functions for rows or columns. And we see that the mean test 1 score is 84 2/3. The mean test 2 score is 90. We also get the means for Alice, Bob, and Carrie. Although note here, and I think they try to emphasize it with the plural, is that we're getting the mean of each row by saying row means, which again gives us our mean column, or vice versa for col means. R is also like Octave in that appearances of mutating data don't necessarily actually do that, but make copies instead. But we'll skip actually showing it to get back to a different kind of naming we can do in Python. Here I'm using the PyTorch library and its tensor type, rather than the array function from NumPy. PyTorch acts a lot like NumPy, but it does have the ability to name your axes, as opposed to in R, where we named our rows and columns. So I print out my scores here, then I can print the mean across test, meaning erasing the test axis, or my mean for student, meaning erasing the student axis, or reducing across it. Here they're warning me that named tensors are experimental, but I'm using them for now anyway. And so we see here that having done the mean across the test axis, all that's left is the student axis, and here are their scores. And one of the reasons you might care about this is not just for simple cases like the test and student here, but for the more complicated cases as well, where you might have up to 4 dimensions, for example. And some people actually do mix up whether batch goes first or last in your dimension list. The bigger you get, the harder it is to keep track of what a number means. So now we have a good sampling of multidimensional arrays across a variety of languages. Maybe we'd want to go more dimensions here, like multiple sections of our class, but there might be different numbers of students in each section, which leads us into things like relational database schema design, or data frames, or entity component systems, arrays of structs of arrays, and many other things out there, which we won't have time for today. Anyway, I hope this has been fun. If you liked the video, be sure to subscribe.
Farvel.